Hey everyone, so we are into chapter 15. We only have 4 chapters left, which means you have 2 tests, and your next test is all about acids and bases. It's chapter 15, chapter 16, which covers anything and everything acid-base. But this is just kind of our introduction to acids and bases. We talked a little bit about this last year, so some of this will be a review, but it's always good to have a refresher. So when we're looking at acid-base equilibria, we're going to ask ourselves, what is an acid or a base? We have this Arrhenius definition, which is what we used usually back in regular chemistry, which is an acid donates an H plus ion and a base donates an OH ion. So those were our typical descriptors of we knew it was an acid if it started with an H, and we knew it was a base if it ended with an OH. So that was our old school definition, but now we got to be using a new definition, a more accurate definition, which is this Bronsted-Lowry definition, and that's the definition we're going to be using from here on out. Acid donates a proton in water, base accepts a proton in water. And what is that proton? It's just a hydrogen atom, an H+. That's what that proton is. So what we're going to be doing is we're going to be looking at some equations. We're going to be seeing what's happening between certain compounds, what's happening to that hydrogen atom, and that's going to determine if it is an acid or a base. So here we have a reaction of nitric acid and water, and we're going to be identifying the acid, the base, the conjugate acid, and the conjugate base. What is conjugate acid and conjugate base? Well, if it starts off as an acid in the beginning of the reaction, what it's going to turn into is the conjugate base. So after that acid donates its proton, it is now no longer acid, it is a conjugate base. The base likes to accept a proton. So after it accepts that proton, it is no longer a base anymore, it becomes the conjugate acid. So acid becomes the conjugate base, base becomes the conjugate acid. They work in inverse there a little bit. So here we're looking at this reaction again. We're identifying acid base, and conjugate acid. And we got to go off of that Bronsted-Lowry definition, which is an acid donates a proton, a base accepts a proton. And remember that proton is our hydrogen. So we're looking at this, and I'm looking to see what happens to nitric acid here, okay? Nitric acid, it goes from HNO3, and it looks like it becomes NO3 negative, right? So from HNO3 to NO3 negative, what happened? It lost its hydrogen. It donated it. So if it donated its hydrogen, that means that this guy is the acid. Okay? Again, you look at the pairs. We got H2O and 3O+, those are the pairs. We got HNO3 and NO3, those are the pairs. And you could notice from HNO3 to NO3-, it got rid of its hydrogen. So it's the acid, which means that the NO3 must be the conjugate base. Right? HNO3, NO3 taken care of. Water. So it went from H2O to H2O+. It ended up gaining a hydrogen, right? From reactants to products, it gained a hydrogen, so it accepted. So that means that the water is acting as our base. That means H3O+ must be a conjugate acid. Okay, so that is what we're going to be doing. That's what they like to ask you on the AP chemistry exam, is identify acid base, conjugate acid, and conjugate base. Let's go ahead and let's do another one. So here's our next one. Again, we're identifying the acid base, conjugate acid, and conjugate base. Let's look at NH3. So it looks like it goes from NH3 to NH4+. Well, what happens in that time? Well, it looks like it gains a hydrogen. It becomes a proton acceptor. So that means that this guy is our base. Well, that means that it must have became the conjugate acid, okay? So, base to conjugate acid. Let's look at water. We already know what it is, but let's go through the process, right? H2O to OH-, it looks like it lost an H+. It donated a proton or H+. So this is our acid. and this is our base. Not base, conjugate base. There we go. Okay, so as you can see, acid base on the left side, conjugate acid, conjugate base on the right side. Now, if we look at this one and our last reaction of HNO3 with H2O, let's just take a look at this and notice what was on the products and reactant side. So, if you notice that this one had a H3O plus on the product side, and this one has a OH minus on the negative side. Let's talk about those guys. That H3O plus is a hydronium ion. Hydronium ion. It's usually what you see in an acidic solution. If you ever see a hydronium ion on the product side, this is an acidic solution. What is that OH minus? That is a hydroxide ion. Okay? If you see a hydroxide ion on the product side, that means that solution is basic. So I'm going to be saying hydronium ion and hydroxide ion a lot. Make sure that you know what I'm talking about when I say hydronium ion, because that's actually what's going to be determining our pH in later lessons. So, again, water, it could kind of act as an acid or a base. Right? See here it donates a proton, here it accepts a proton. So water can act as both. So be aware it could become a hydronium ion or a hydroxide ion. This one is in basic solution because we have OH on the product side. This one is an acidic solution because we have an hydronium ion on the product side. I just want to do two more examples here where we identify acid base, conjugate acid, and conjugate base. Let's look at this top one. I got H2PO4 and it goes to HPO4 2 minus. So from here to here it lost a hydrogen, it lost a proton, so it donated a proton from reactant to product side. So that means it is an acid. So this guy must be our conjugate base. Water, I look at it, it goes from H2O to H3O plus. It gained a proton, it gained a hydrogen. So that means water is our base, and this is our conjugate acid. Let's go ahead and look at this next one. PO4 to 3 minus to HPO4 2 minus. It gained a proton, right? It accepted one. Remember, a proton acceptor is a base. So that means that this must be our conjugate acid. If we look at H2O to OH minus, it got rid of a hydrogen atom. It donated a hydrogen atom, so it must be our acid, and this must be our conjugate base. Right? Here's another type of question I might ask you. Let's say that I just don't give you an equation at all, and I ask, what is the conjugate base of H2S? Okay? What is the conjugate base of H2S? So I give you a compound, no equation whatsoever, and you got to tell me the conjugate base. Well, what is conjugate base usually paired with? Acid, right? An acid becomes a conjugate base. So if we're asking what is the conjugate base of H2S, that means that we must be treating H2S or hydrosulfuric acid as an acid. Okay? So we're going from acid to conjugate base. So what is the conjugate base of the acid hydrosulfuric acid? Well, remember, acids donate a H plus or a hydrogen. So this guy is going to become HS minus. So this was originally the acid. This is now the conjugate base. All right, I will ask you questions like that. What about this one? What is the conjugate, let's switch it up now. What is the conjugate acid of NO3 minus? I know you guys love that squeaking noise. What is the conjugate acid of NO3 minus? Well, remember what goes with conjugate acid? Base. So that means we must be treating this guy as a base. And remember, bases accept a proton. They accept an H+. So that means that the conjugate acid for this guy must be, thought I was going to sneeze, HNO3. Okay? So be ready for that, and that is all we're going to go into with Bronsted-Lowry. Let's go into our dissociation equations that we have to be able to do. Alright, so one concept that you have to understand is that acids donate one proton at a time. They will never donate multiple protons at a time. So let's look at something like HCl. This is known as a monoprotic acid. It only has one hydrogen. So when you hear monoprotic, that means it only has one proton it could donate. And this only has one proton because it is HCl. So when it dissociates, as an acid does, it's going to be H+ and Cl-. It got rid of its one proton. Let's look at a diprotic acid though. Something like H2SO4. H2SO4 is a diprotic acid because it has two protons. It's got two hydrogens. But once again, it is only going to donate one proton at a time. So it is only going to separate from one of its hydrogens, which means that we have HSO4 minus as our remaining, I suppose that would be our conjugate base. So again, it's never going to be something like 2H plus SO4 2 minus. It's not going to do that because that's donating two protons at a time. It's only going to donate one at a time. Now this guy could go ahead later on and donate its proton, but it's never going to get rid of both of them at the same time. Now let's look at a polyprotic acid. Something like H3PO4. It's polyprotic because it has multiple hydrogens. More than one or two, it's got three. So this is a polyprotic. So monoprotic, diprotic, polyprotic. But again, it only donates one hydrogen at a time. So it's going to get rid of its H+, and it is going to form H2PO4-. So please understand that basic concept of hydrogen just giving up one H+ at a time. So we got to be able to draw these dissociations, these guys breaking apart, dissolving. And how you're going to do it is there's always going to be an H+ separating from it. Just one, never two, just one. Let me show you some different versions of these dissociation equations that you'll see. Okay, and where you might think this is confusing, but it's really just a simplification. So we have the dissociation of hydrochloric acid right here. Well, you might also see people write it as this equation right here. And you might be saying, okay, those are totally two different equations. They are pretty much saying the same thing. All acids are in water, so usually all equations in their actually unsimplified form look like this. HCl plus H2O becomes H3O plus and Cl-. But scientists get so tired of writing that water in there that they just omit it, because water really doesn't affect equilibrium, right? Because it's in liquid form. So what they do is they just simplify it to this top reaction like so. So what that means is that H plus and H3O plus, they are the same thing. You will see in science that they interchange H plus and H3O plus all the time. Please note that they are the same thing. Okay? When we do our acid-base calculations, we will take the negative log of H plus to get pH. You could take the negative log of H3O plus to get your pH as well. Another example of this, like what we were just talking about before, is say we had that H2SO4 with water. Okay? In the non-simplified version, it'll be H3O plus and HSO4 minus. But again, scientists are a little lazy and they'll just omit the water altogether and they'll just write it with just getting rid of its proton without the water included. But they are essentially the same type of reaction. So let's go ahead and write the Ka for these. What is Ka? Ka is just like our equilibrium expression of Keq or Kc or Kp. Ka tells us how much something dissociates. So if we are going to go ahead and once again look at this, it might have a Ka of say 1 times 10 to the 10th. Okay? This has an equilibrium expression much greater than 1, which means that HCl is going to dissociate a whole lot into H plus and Cl minus. That's what makes HCl a strong acid. It likes to break down into its ions and eat away at other ions, such as your skin. Okay? So if we are going to draw or write the equilibrium expression for this, these are all aqueous. All acids are aqueous. So our equilibrium expression for this is once again just going to be products over reactants. Our concentration of H plus and Cl minus over our concentration of HCl. Right? So just like in our equilibrium, a lot of this stuff carries over to acid base. Okay? So we are going to be writing a lot of these equilibrium expressions. Remember, the higher the Ka, the more it's going to dissociate, so the stronger the acid. A weak acid, say like HF, it will dissociate slightly, okay, but it is a weak acid, so it might have a Ka similar to, let's go with 1 times 10 to the negative 10. It is not going to dissociate a lot, okay? And again, that just goes back to our equilibrium. If it's greater than 1, it will break apart. It'll go to those product sides. If it is less than 1, it won't break apart and it'll stay more as a reactant. All right, so let's go ahead and talk about those strong acids. All right, I said this at the beginning of the year and I mean it now. We have to memorize these strong acids and strong bases. These strong acids and bases have a really large Ka, which means they dissociate completely. And that will come into play when we do our calculations, like our negative log. These strong acids and bases do not require you to use an ice table. We'll have to use ice tables later on. But these acids just require our standard calculations that we'll get into later of negative log of H plus equals pH, or negative log of OH minus equals POH, or 10 to the negative pH equals H plus. This is where we can just use simple calculations. So please understand and know these strong acids and strong bases. Write them on a piece of paper somewhere, put them on your computer screen so you can see them every day. So when you see them on the AP exam, you know which ones are the strong ones and which are the weak ones. So again, I just want to enunciate this some more, is that these strong acids and bases, when they are put into water, they dissociate completely. There's only going to be ions in here. There's not going to be any HCl as far as we're concerned, for simplicity's sake. But our weaker acids, like ones like hydrochloric acid, they aren't going to dissociate a whole lot. They want to stay together. HF are both elements that really want to react, okay, and they're really small, so they stay close together. They don't dissociate so much, but they will dissociate just a tiny bit. Okay, but get that through your brains, okay? Strong acids dissociate a lot. Weak acids and weak bases don't dissociate a lot. All right, so what does that mean as far as Ka goes? Well, let's just look at some Kas and some Kbs real quick and write those. So let's look at a Kb instead. Let's look at something like let's go with let's go with NH3 plus H2O and NH4 plus and OH minus. Okay, and I want you to write the equilibrium expression for this. Well, this is a base, okay? This is a base because it accepts a proton. Okay, so we are not writing a Ka, we are writing a Kb for this one. Again, that A and B don't really matter. It's expressing the same thing. It's just stating to you that the B is a base and the A is an acid. And once again, we are going to put products over reactants. So we're going to go ahead and we're going to put our NH4 plus and our OH minus on top. Oops. And our NH3 on bottom. We're not going to put H2O because it's a liquid and it does not affect equilibrium. Alright, and the same thing with Kb is with Ka. If it's a really large Kb, like 1 times 10 to the 10th, it dissociates a lot. It's a strong base like NaOH, KOH, or LiOH. If it's got a really, really small Kb, it's a weak base. This is NH3. It's not one of our strong bases. It's going to be a weak base. It'll probably have more of a Kb by 1 times 10 to the negative 10th or something similar like that. So let's go ahead and let's put some of that Ka knowledge to the test. So what we have here is a list of acids and their Kas. And what I want you to do is I want you to rank them from weakest to strongest based on their Ka. Remember, I stated that the higher the Ka, the more it dissociates. The more it dissociates, the stronger it is. So let's go ahead and let's start with our weakest. What is going to be our weakest acid here? Which one has the lowest Ka? Which one's not going to dissociate very much? Well, if we're looking at this and I look at my Kas, it looks like the smallest one I have is HCN. So this guy is going to be our weakest. All right, we'll cross him out. So we're going to go look at our next one. What is our next smallest number? I got 2 minus 4s here. I got 7.2 to the minus 4 and 4.0 times 10 to the minus 4. Well, this one's smaller because the leading number is 4 smaller than 7.2. So our next one is nitrous acid, HNO2. And then our next one will be hydrochloric acid, which is HF. Leaves me with water and HCl, and you could probably just use your knowledge of chemistry to figure this out, but let's go ahead and look at the Ka. Ka of H2O is 1. Ka of HCl is 1.3 times 10 to the 6th. This is much larger than 1. So our next one is going to be H2O, and our last one is going to be HCl. And then if I asked you to go ahead and rank these from weakest base to strongest base, it'd just be the opposite. This would be our weakest base, and this would be our strongest base. They work inversely, okay? So please understand that Ka reflects how strong an acid is. The higher the number, the more it dissociates, the more it's able to react with other ions. Let's talk about one more thing about H2O. Okay, I just want to let you know that H2O is this fancy science word of amphoteric. Amphoteric or amphiprotic is what they'll say. But amphoteric, what does that mean? It can act as an acid or base. Okay, water's special that way. It can act as an acid or base, right? Water can donate an H3O plus, okay, or it could accept a H3O plus and be a base, or it can donate an H plus and become an acid. Okay, so both of these are acids and base. That's what amphoteric means. Sometimes they will ask you, is this or which one of these compounds is amphoteric? And it's usually a 1 that can donate a H or accept an H. A common one is HSO4 minus, right? It's pretty amphoteric. It can accept an H plus and become H2SO4, or it could donate an H plus and become SO4 2 minus. So that is our intro to acid bases. Make sure you know how to list acid base, acid, conjugate base. Make sure you know your strong acid, strong bases. Make sure you know how to write a Ka and a Kb expression. Remember that how to write those dissociations of strong acids. You could include water or you can not include water. It does not matter. H3O plus and H plus are the same exact thing. Know monoprotic, diprotic, polyprotic acid, and know what amphoteric means. That's it, guys. If you have any questions, let me know. Have yourselves a great day.